Welcome to today's lecture on energy balances on non-reactive processes with phase change. So, in the last lecture we performed some tutorial problems. Today we will be continuing with those tutorial problems. As promised, today we will be solving a system which is a closed system. Until now the problems which we looked at have all been open systems and we have been using enthalpy. So, today we will actually look at a closed system where we will be using internal energy for performing energy balances. Just to refresh your memory, so why do we use internal energy for closed systems and why do we use enthalpy for open systems? If you remember, the general energy balance equation we start off with based on the first law of thermodynamics for a closed system is Q minus W equals delta U plus delta E K plus delta E P. So, this work term which is W can have two different components, one is the shaft work and the other is the flow work, and this shaft work is due to moving of a shaft which could be rotating something, and flow work is the work associated with the moving the system boundary which is the PDV work. So, the flow work is important in an open system because material is flowing in and out, and therefore, the flow work accounts for this equation and the equation becomes Q minus Ws equals delta U plus Wf plus delta Ek plus delta Ep. As flow work can be written as PDV, so delta U plus P delta V would become delta H, giving you enthalpy, and this would be the equation for an open system. In an open system, because there are flow rates and rates are used instead of masses or moles, we would write these as Q dot minus Ws dot equals delta H dot plus delta Ek dot plus delta Ep dot. So, for an open system we have been using this equation as the general energy balance equation. For this reason we always calculate specific enthalpy and then the total change in enthalpy. However, today we will be looking at a closed system, so we will be using this equation. So, where you use specific internal energy instead of specific enthalpy and then finally calculate change in internal energy to understand how much heat is required. So, this is applicable for closed systems at constant volume. If there are closed systems with constant pressure, what you would have is a change in volume. When there is a change in volume, the work term W would have either a shaft work and also it will have a work associated with moving the system boundary. So, this moving the system boundary would be the PDV work, and to account for this PDV work we again have to convert the internal energy to enthalpy. So, that is why when we have a closed system with constant volume we use internal energy, and for a closed system with constant pressure we use enthalpy. For an open system we would always use enthalpy for energy balance calculations. Now that we have quickly refreshed the fundamentals, let us look at the tutorial problem for today. A liquid is placed in a well insulated container which is then sealed. Initially the container and its contents, which is liquid and pure nitrogen, are at 93 degrees Celsius and 1 atmosphere. The liquid volume is 70 centimeter cube and the gas volume is 3 liters. The liquid partially evaporates and the system cools down and eventually comes to thermal equilibrium at 85 degrees Celsius with liquid still present. Physical property data for the liquid and its vapor are given here. You are asked to estimate the CV values for the liquid and the vapor, and you are also asked to calculate the mass of the liquid that evaporates by assuming 4.97 calories per mole degree Celsius as the heat capacity of nitrogen. So, for this problem we do not know what the liquid is, so we have just been told it is a liquid, so we will just call it as liquid A. So, this liquid A is present along with nitrogen in a closed system. So, it clearly states that it is placed in a well insulated container and sealed. So, this is before the process starts. So, at the start of the process you have the liquid and nitrogen charged into a closed system. This is at 93 degrees Celsius and 1 atmosphere pressure, and after this basically some of this liquid evaporates and there is an equilibrium which is reached. after some of the liquid evaporates, you would have a gas phase which would have a mixture of nitrogen and the vapor component of this liquid A, and the volume of the liquid would have come down. So, now we need to perform required energy balance calculations and material balance calculations to identify whatever has been asked for, which is finally the mass of the liquid that evaporates from the liquid which has been charged. So, before we start doing this, we have also been asked to calculate the CV terms. Why do we need CV? As I already said, for this problem, being a closed system, we will be looking at calculating change in internal energy. Change in internal energy can be calculated for temperature change processes as integral CV dt. So, we need to know the CV values. Here in the problem, we have been given the CP values. So, we have to calculate the CV values from these CP values. In one of the earlier lectures, we have actually discussed how CP and CV can be correlated. For liquids, CP equals CV, and this is an approximate equal, and this is a good approximation to use, and for gases, for ideal gases, it is Cp equals Cv plus R. So, these are the two correlations which we have been told. So, using this we can calculate the Cv of the liquid and the vapor phase of component A. So, Cp of liquid is given as 20 calories per mole degree Celsius, and Cp of vapor phase is given as 10 calories per mole degree Celsius. Using this, we can calculate Cv of the liquid component A as equal to Cp of the liquid component, which is 20 calories per mole degree Celsius. Cv of the vapor phase would be equal to Cp of the vapor phase minus R. So, here R would be used in terms of calories per mole degree Celsius. So, which means it would be roughly 2 calories per mole degree Celsius. Using that, we would have 10 minus 2 equal to 8 calories per mole degree Celsius. So, this would be the Cv value for vapor. So, with this we have the Cv for the liquid and the vapor, which is the first part of the problem. For the second part of the problem, we have to do the required material balance calculations. So, first thing we know is there are N0 moles of nitrogen and N1 moles of component A present in the initial condition. So, this out of this N1 moles, some of the liquid A evaporates. So, let us assume N2 moles of A has evaporated and mixed with N0 moles of nitrogen in the gas phase, and you have liquid component of A as N3 moles. So, we need to calculate what N0, N1 and N2 are to identify how much has actually been evaporated. First, to calculate N0 moles, we have to use the ideal gas law. Assuming ideal gas behavior for nitrogen, we can calculate N0 as PV by RT. So, we have been told that the condition, the temperature conditions is 93 degrees Celsius. So, which means the temperature T would be 93 plus 273 Kelvin, and you have volume as 3 liters and R would be 8.314 and P pressure is 1 atmosphere. Applying all this, you will be able to calculate N0 as 0.1 moles of nitrogen. So, this would be the number of moles of nitrogen which is present in the initial condition and also in the final condition. So, both are N0 moles. We now have to calculate the number of moles of component A which is present in the liquid form in the initial condition, which is N1 moles. So, to calculate N1 moles, we have the volume and we have also been given the density of component A. So, using that we can convert it into mass, and we have the molecular weight of the component A. So, because of that we can calculate the number of moles of component A. So, let us first calculate the mass as volume times density 0.9 grams per ml. So, this is 70 ml, and we have the molecular weight is 42 grams per mole. So, we would have this dividing it by molecular weight, we would be able to calculate the total number of moles. So, ml gets cancelled, grams get cancelled, and we end up with number of moles. So, N1 equals 1.5 moles of A. So, the total number of moles of component A present in the liquid component would be 1.5 moles at the initial condition. Some of this gets evaporated to form vapor phase in the final condition. To find out how much has evaporated, we would not be able to use any material balances, because the material balances would all be trivial. So, instead we could perform energy balances to calculate the amount of component A which has evaporated. So, how would we go about doing that? First thing would be to identify whether this is an open system or a closed system. As I have been telling from the beginning of this lecture, so we are looking at a closed system. So, we will be using internal energy in the energy balance equation. So, the energy balance equation becomes Q minus W equals delta U plus delta Ek plus delta Ep. So, here there are no moving parts. So, W would go to 0, you have Ek and Ep going to 0 because there is no change in kinetic and potential energies. So, you will be left with Q equals delta U. In addition to the general cancellations which we have done, the problem also states that the system is well insulated, which means there is no heat being transferred from the system to the surroundings or vice versa. This would imply Q is also equal to 0. So, the equation then becomes delta U equals 0. Now, by building a specific internal energy table, we will be able to calculate the number of moles of component A in the liquid and the vapor phase in the final condition. Let us go ahead and do that. To build this internal energy table, we first need to identify the reference states. We can either use the initial condition or the final condition as the reference states. So, here for the calculations I have used the final conditions as the reference state. So, the reference states used are nitrogen gas 85 degrees Celsius and pressure P atmospheres, and you also have component A. I am assuming the liquid phase of the final condition, which is liquid phase 85 degrees Celsius P atmospheres as the reference state. So, here I am taking P atmospheres, which is the final condition, as the reference state. We have the final condition as pressure as P atmospheres. So, pressure P atmospheres to the initial condition pressure 1 atmosphere indicates that there is a change in pressure. However, because we are going to assume ideal gas behavior and we have a liquid as the other component, we can ignore change in internal energy due to change in such small pressures. So, because of this, we will assume that pressure has no effect on our calculations and we will only look at change in temperature and change in phase. So, using that assumption, let us build the internal energy table. So, the components would be nitrogen, component A as liquid phase and component A as vapor phase. As I had already mentioned, we should always list out components of different phases separately while we are writing these enthalpy or internal energy tables for phase change operations. In this table you have N initial and U cap initial. So, instead of enthalpy we are using internal energy, and you have N final and U cap final. So, which would be the internal energy, specific internal energy for the final condition. So, we have 0.1 moles of nitrogen coming in, and nitrogen in the initial and the final system, and we have 1.5 moles of component A present in the liquid form in the initial system. We have N3 moles of liquid component A in the final system and N2 moles of vapor component A in the final system. We do not have any vapor component A in the initial system. Now that we have this, we have to identify which specific internal energies have to be calculated. So, for the final condition, which is gas 85 degrees Celsius and pressure of P atmospheres, the nitrogen would have 0 internal energy as compared to the reference state. Similarly, A, which is liquid 85 degrees Celsius and P atmospheres, would also have 0 in specific internal energy change from the reference state. However, the final condition for A vapor would have an internal energy that needs to be calculated, and similarly you would have internal energies for these two terms that have to be calculated. So, we are calling them U1 cap, U2 cap and U3 cap. So, we need to account for U1 cap, U2 cap and U3 cap. So, U1 cap is basically change in temperature for nitrogen gas from 93 degree Celsius to 85 degree Celsius. So, it is nitrogen. So, this is U1 cap. So, U1 cap is basically nitrogen gas at 85 degree Celsius and P atmospheres going to nitrogen gas 93 degree Celsius and 1 atmosphere. So, assuming that pressure has no effect, you would end up with only change in temperature. So, this means U1 cap would be equal to integral Cv dt with the limits of 85 degree Celsius to 93 degree Celsius, and this can be calculated for nitrogen, and we would be able to get this value as Cv times 93 minus 85, which is equal to 39.8 calories per mole. So, similarly we can calculate U2 cap as integral Cv dt. So, again here it is only a process where component A, which is in liquid phase 85 degree Celsius and P atmospheres, which is the reference state, goes to A as liquid at 93 degree Celsius and 1 atmosphere. Again ignoring the effect of pressure, the equation, the process is only change in temperature. So, going from 85 to 93. So, we already calculated the Cv for the liquid component A. Using that, we would be able to use and calculate the change in internal energy U2 cap for this process. So, this would be 160 calories per mole. Now, the third component, which is U3 cap, is where you have the phase change also. So, what information do we have? In the problem, we have been given delta H cap V, which is the enthalpy change associated with vaporization. Here we need to calculate the internal energy change associated with vaporization. If you remember, we have looked at this and we have identified this as delta H cap V would be equal to delta U cap minus RT. If you look at the problem gives you delta H cap V, which is the enthalpy change associated with vaporization. However, in this calculations we are using internal energy. So, we need to find out what would be the internal energy change associated with the vaporization process. So, we have already looked at what the difference would be, how we can actually calculate delta U cap V from delta H cap V in the introduction lectures. So, how would we do that? The correlation between delta U cap V and delta H cap V would be similar to the correlation you have for delta H cap and delta U cap. So, you would have the PdV P delta V term, and assuming ideal gas behavior, we would be able to convert it into RT term. So, this would mean that your delta U cap V would be equal to delta H cap V minus RT. So, we can calculate delta U cap V as delta H cap V minus RT, where T would be the temperature at which the phase change happens. In this problem, we have been given delta H cap V at 90 degrees Celsius is equal to 20,000 calories per mole, and we can use this and calculate delta U cap V and perform calculations. So, your delta U cap V would be equal to this 20,000 minus R in terms of calories would be 2 times temperature, which would be 90 degrees Celsius or 363 Kelvin. So, this value would be 19,274 calories per mole. To calculate change in internal energy U cap 3, which we would have to assume the process where component A basically goes from the reference state, which is liquid 85 degrees Celsius, to A, which is vapor at 85 degrees Celsius. So, for this we would have to build a hypothetical path. We have only phase change happening, however, we do not know the change in internal energy or enthalpy for the phase change at 85 degrees Celsius. We know that only for 90 degrees Celsius. So, we need to build a hypothetical path where the phase change happens at 90 degrees Celsius. So, that would mean the process would be A, which is liquid at 85 degrees Celsius, goes to A as liquid at 90 degrees Celsius. From here it goes to A as vapor at 90 degrees Celsius, and from here it goes to A as vapor at 85 degrees Celsius. Again I am ignoring the effect of pressure for doing these calculations. So, we have 3 different internal energy changes, one with delta T, other with change in phase, and the last one with again change in temperature. So, here we will be using the CV for liquid for the initial calculations and CV for the vapor for the second calculations. So, your U cap 3 U3 cap would be equal to integral CV dt from 85 to 90, where here you are using the CV of liquid, plus delta U cap V, where the phase change from liquid to vapor is happening, plus integral 90 to 85 CV of vapor dt. So, CV of liquid was identified to be 20 kilocalories, sorry 20 calories per mole degree Celsius times 5. So, 20 times 5 plus the change in internal energy was 19,274, plus here you would have CV as 8 times 85 minus 90, which is minus 5. So, this U3 cap would be equal to 19,334 calories per mole. These values can be plugged back into the specific internal energy table which we prepared, and we can calculate the total change in internal energy and fit it back into the general energy balance equation, which states delta U equals 0. So, using that we would have a correlation which would have one unknown, which would be the number of moles of vapor component of A in the final condition. So, N2 would be the only thing which we need to calculate from here. So, what we would do is the equation delta U equal to 0, which would be equal to final minus initial. So, final would be N2 times 19334 minus initial, which is 0.1 times 39.8 minus 1.5 times 160, and this would give us an equation for N2, and from here we can calculate N2 as 0.0126 moles. So, this means 0.0126 moles of the initial liquid component A has evaporated, and this would be the amount which has entered into the gas phase in the final state. So, with this we have performed the required energy and material balance calculations to find out all the components that have been asked for. So, this number of moles can also be converted to mass, because we have been asked to calculate the mass of gas which liquid which has been evaporated. So, N2 times the molecular weight would give you the mass, which is equal to 0.0126 times 42, giving you a value of 0.53 grams. So, 0.53 grams has actually evaporated. So, with this we come to the conclusion of this tutorial session. So, in the next lecture we will look at something called psychrometric charts. So, in just like how we use steam tables, there are charts which can be used for 2 component systems, and psychrometric charts are basically humidity charts, where you have 2 components and the information related to specific enthalpy and other things like humidity, so on, can actually be obtained from these charts. We will look at how to use these psychrometric charts in the next lecture. Thank you.